Hello. So in the last video we established a couple of things, okay? One of them being the components of the two wave functions. Where x was less than 0, we had psi1 of x is equal to a e ik1x plus b e to the minus ik1x. And where x is greater than 0, we had psi2x is equal to c e ik2x, where a, c and b are constants, okay? A e to the ik1x represents the incident wave. This term represents the reflected wave, and this term ce to the ik2x represents the transmitted wave. Okay, I explained that in my previous video. So today we're going to calculate the probability of reflection or transmission. In other words, we're going to calculate the probability of the particle being reflected by the potential step or being transmitted through the potential step. Okay, so you can calculate the probability that the particle will be reflected or transmitted through the step by calculating the reflection and transmission coefficients. Okay, these are defined in terms of something called the current density Jx. Okay, this is the current density Jx. Okay, this is given in terms of the wave function. So the current density is equal to IH bar. This is a definition you might want to learn. IH bar over 2m multiplied by psi of x multiplied by the derivative of psi. So I'm going to put, let's put prime star x just to simplify notation. That's the derivative of the complex conjugate of the wave function minus the complex conjugate of the wave function, like that. And then we multiply the derivative of the ordinary wave function. Okay? Alright, so wave function multiplied by the derivative of the complex conjugate minus the complex conjugate multiplied by the derivative of the wave function. Okay, that's the current density. So, if JR, okay, JR is the reflected current density and Ji is the incident current density, okay, Ji is the incident current density, then R, the reflection coefficient, is simply a ratio, JR divided by Ji. Okay, that is the reflection coefficient. The transmission coefficient is very similar. It is the current density for transmission divided by Ji. Alright? Okay, so you now have to calculate JR and Ji and JT. Actually, that's not so hard. Let's start with Ji. Because the incident part of the wave is A e ik1x, okay, the incident current density is simply going to involve this term here. That's all we need in our calculation. Okay, so let's write this out. So first of all, we know that we're dealing with the instant current density, so we're going to look at psi ix is equal to A e ikx. Okay, that's a 1. Now that's what we'll be dealing with. So first of all, let's calculate the complex conjugate of psi ix. Okay, the complex conjugate, okay, simple differentiation. Okay, that's simply going to be AE minus ik1x. Okay, sorry, not differentiation. We're taking the complex conjugate. Yes, so complex conjugate would just change the sign of the I. Sorry, we're not differentiating. Okay, but now we are. So take the derivative of psi ix. The derivative, okay, that's simply going to be using the chain rule. So ik1 a e to the ik1 x. Alright? Now we take the derivative finally of the complex conjugate. So prime complex conjugate Okay, this is my own notation just to simplify things down, by the way. So a prime is just the derivative. Take the derivative of the complex conjugate, you bring down the constant using the chain rule, you're going to get minus I k 1, is it? Yeah, it's 1 a e to the minus I k 1x. That's all we need to plug into our formula for current density, okay? In this case, we're looking at the incident wave, okay? Right, so that's good. So we put that into the formula, okay? This will take quite a while, but we're going to get IH bar over 2m, okay? And we multiply that by, first of all, our ordinary wave function, which was a e to the I k1x, okay? Then we multiply that by the derivative of the complex conjugate, which was minus I k1 a e to the minus I k1x. Okay, and then from there, we minus the complex conjugate of the wave function, which is simply this, minus I k1x, and then multiply by the derivative of the ordinary wave function, I k a e, so 1 I k1x. Alright, and that is your formula. So all we need to do is simplify that down. Okay, so this is equal to IH bar over 2m. Okay, so what we have here, we're going to get minus IKA squared 1 minus IKA squared. Okay, you can see that? Right, and then simply what we can do is we have, this is equal to IH bar over 2m multiplied by, of course, put these together, we're going to get minus 2k1a squared. Okay, so obviously the 2's cancel out. Okay, and what we have is that this will give us h bar k1 over m times a squared. Okay, brilliant. And that is it. That is the current density. Okay, and this works the same way for JR and JT. So this is looking at the incident current density. This works for the same for JR and JT. JR is equal to h bar k1 divided by m times b squared, and for JT is equal to h bar k2 m c squared. Okay, it works the same way. Okay, of course you've got different constants depending on if it's incident or reflected or transmitted. Okay, I hope you understand that. You can pause the video here just to see what I did. I don't have enough time to go through the whole calculation, but it's basic algebra here. Okay, right, brilliant. So overall, okay, you should be able to get that R, the reflected coefficient, R is equal to JR divided by JI, and that's of course equal to B squared divided by A squared. This is because simply the IKM will just cancel out with each other on top. Okay, of course the constants are different, so they won't cancel each other out. Okay, that squared should be there. Right, so, and finally, T, the transmission coefficient, is equal to JT divided by JI, and that's equal to K2 multiplied by C squared divided by K1 A squared, okay? K2 and K1 are different, so they don't cancel each other out. Okay, so there you have it. So in the next video, we're going to try and find A, B, and C.